Good morning, and this is P. Shivashankarajamani, Associate Professor, Department of ECE, KSR College of Engineering. So today I will be handling circuit theory. In the circuit theory, I will be discussing about Thevenin's theorem, especially. The outline of my presentation is introduction, theorems, what are theorems, why we go for Thevenin's theorem, statement of the theorem, steps to analyze Thevenin's theorem, solved problem, one problem is being solved, and the online demonstration of the theorem, application of the theorem, a recap and sum up. So this is my outline. Introduction. So a large complex circuits can be converted into a simple equivalent circuit with the help of circuit theorems. Circuit theorem consists of Thevenin's theorem, Norton's theorem, superposition theorem, maximum power transfer theorem, and reciprocity theorem. Why we want to go for Thevenin's theorem? This Thevenin's theorem simplifies the circuit analysis. It reduces the complex circuit into a simpler equivalent circuit, especially useful when you analyze a specific component or a load. So easily repeated calculations. If you need to calculate the response of a multiple load resistance, Thevenin's equivalent circuit saves time, as the equivalent circuit remains the same while only the load changes. Facilitates problem solving. It provides insight into how the rest of the circuit behaves as a source and separates the effect of the load. Improves understanding, breaking up complex systems, makes it easier to understand the behavior of individual components. Statement. Any linear complex electrical network with voltage source, current source and resistance can be replaced by a pair of terminals by an equivalent circuit consisting of single voltage source, which is called as Thevenin's voltage, VTH, in series with a single resistance called Thevenin's resistance. Note, so in order to find your voltage source VTH in series with your resistance RTH. VTH, other name is called as open circuit voltage at the terminals, and RTH is the equivalent resistance of the terminals when the independent sources are turned on. So here we have a theorem. So we have a linear two-terminal circuit which has been converted into a voltage source in series with your resistance. So voltage source we call it as VTH or VOC in series with your resistance RTH or looking back resistance. Steps to analyze Thevenin's theorem. First step, remove the load resistance RL. Second point, calculate the open circuit voltage. This open circuit voltage is called as Thevenin's voltage or VTH. Step 3, calculate the open circuit resistance. This is called as Thevenin's resistance RTH. Step 4, open circuit when you have the sources, current sources. Short circuit when you have the voltage sources. Now redraw the circuit with the measured open circuit voltage, which is VTH, which has been found in step 2, and measure the open circuit resistance RTH, which has been found in step 1, which should be connected in series with the resistance connected to the load. We have removed in step 1. This is the equivalent Thevenin circuit of a linear electrical network or a complex circuit, which had been simplified and analyzed by Thevenin's theorem. To find the current flowing through the load resistor, you can use Ohm's law. So I of t which is equal to VTH divided by RTH plus R. So in order to find the Thevenin's voltage VTH, the other name is VOC, remove the load resistance RL, get the open circuit voltage across AB, and this is called as Thevenin's voltage or open circuit voltage VOC. Now we have to find the Thevenin's resistance RTH, remove the load resistance RL, turn off all the independent sources. If it is voltage source, make it into short circuit. For we can take into account for internal resistance, which can be replaced. If it is current source, it has to be open circuit. This RTH can be obtained by a simplification of either series or parallel, depending upon the connection between A and B. In order to find your load current, so we found that VTH in series with your RTH, and then we have connected the load. So in order to find your IL is equal to its VTH divided by RTH plus RL by using the voltage Ohm's law. So in order to find your VL, that is voltage across the load, so it's IL into RL, so it is RL divided by RTH plus RL into VTH. So we have a simple problem to verify this theorem. Using Thevenin's theorem, find the voltage across AB. Here the load resistance RL is equal to 220 ohms. So we have the resistance 470 ohms and the resistance R2 330 ohms and R3 560 ohms and load resistance RL, which is 220 ohms, which has a total supply of 36 voltage, which has been connected to the cycle. So the first step, remove the load resistance RL. Now we have removed the load resistance 220 ohms. Now the second step, we need to find the VTH. In order to find the voltage, we need to connect a voltmeter, the DC voltmeter, so that we can find the VOC or VTH. Here, the current will not be flowing through this 560 ohm because it is an open circuit voltage. Now the current will be flowing only through R1 and R2. So they both are in series. So 470 ohms plus 330 ohms is the total resistance. So in order to find the total current I of t, so it's V divided by R1 plus R2. So V is equal to 36 divided by R1 is 470, R2 is 330. So if you see that the current, total current is 4.5 milliamps. So in order to find your VOC or VTH, so we have to multiply this 4.5 into 330 ohms. So we will be getting 14.85 voltage. So in order to find your RTH, so we remove the load supply voltage, now we short circuit. So 470 and 330 ohms are in parallel. So it's 470 into 330 divided by 470 plus 330. The total resistance will be in series with 560 ohms. So we could able to see that it is 753.8 ohms. So step 5. So complex circuits can be converted into a simple circuit. So I have block based complex circuit, which can be replaced by a single voltage source, single resistance, which is called as RTH. So single voltage source is 14.85 voltage and single resistance is 753.8 ohms. Now we connect the load resistance RL, just 220 ohms. Now it's been connected, so we want to find the current at load. So IL is equal to its VTH divided by RTH plus RL. So since they both are in series, RTH and RL are in series, we can just add both the resistance. So IL is equal to, it is 14.85 divided by 753.8 plus load resistance 220 ohms. So the current is 15.25 milliamps. So we have converted a complex circuit into a simpler circuit and we find the load current. So here we can keep on changing the various load. If it is load is 330 ohms, so it is remaining circuits will be the same. So IL is equal to VTH divided by RTH plus RL. So it's 14.85 divided by 753.8 plus 330. So if the load only changes, we can easily calculate the load current. So here I am just using an online simulation of DC AC lab simulator in order to show this demonstration. Right, here we could able to see that same circuit is drawn with a battery of 36 voltage, which is connected with the resistance R1 470 ohms and 330 ohms R2 and a 560 ohm resistance, and we have the load resistance RL is equal to 220 ohms. So from this circuit we could able to see that, so it is current flowing is 15.4 milliamps after connecting the battery. Now we will demonstrate how it works for our circuit. So first I am just finding the RTH. Right. So here is the RTH. So in order to find your RTH, remove the load resistance RL. Alright. So here your resistance 470 ohms and 330 ohms are, it is in series with your resistance 560 ohms. So we have this resistance RTH, which is equal to 751.6 ohms. Whereas our theoretical RTH value is 753.8. Right. So here we could able to see that it is 2.4 ohms is lesser because it may be the because of this tolerance value. Now we'll look into the VTH value. And we could able to see that the VTH is 14.9 voltage. Then we will see this, the same circuit as per the circuit diagram, which has been connected beyond this 560 ohms. Here also we could able to see that same VTH, but no current is flowing this 560 ohms. Here also the voltage is it's 14.9 voltage. Then we need to find the load current. So we have the supply voltage of 14.9 voltage. We have the resistance. So we could able to see that it is the multimeter is showing it's 14.9 voltage. It is connected in series with the RTH, is 751, and we could able to see that the current flowing is 15.4 milliamps, which is same as the current is flowing in the before circuit. So application, all the elements remaining unchanged, only the load changes. We could able to analyze the current at the particular load, whether it is decreasing or increasing. Recap, so we could able to see that complex circuits can be converted into simple circuits.